Okay, welcome back everyone to DSC 102. Am I audible to folks at the back? Folks at the back? Yes? No? Yes? Okay, good. So thank you for showing up to this industry guest lecture, or first of the series this quarter. It's a pleasure to have with us Russell Kaplan. He leads products at Scale AI's infrastructure suite. And Russell was the founder and CEO of Helia AI, a computer vision startup that was acquired by Scale in 2020. He was, before that, a senior machine learning scientist on Tesla's Autopilot team. He received his master's and bachelor's from Stanford University, working with Professor Fei-Fei Li in Stanford's Vision Lab. So Scale AI has been making waves in the AI field, in particular data-centric AI. So Russell is going to tell us all about that, and it could be potentially useful for you, both for your projects here and wherever you go after you graduate. So pay attention, data-centric AI is becoming a big deal. Okay, with that, I'll hand it over to Russell.
Thank you so much for the introduction. Give me a sec to clip this microphone. All right, I might just hold it. Great. Oh, I can use the lights. Perfect. Can everyone hear me okay? Great to be here. Thank you so much for having me. Really excited to be back on campus. My name is Russell. Today I'm going to be talking about data-centric AI in practice. All right. So as I go, by the way, please feel free to just raise your hand, interrupt with questions. I really like when lectures are interactive as opposed to everyone's kind of listening and then getting to ask questions at the end. I'll also have time for questions at the end. So a little bit about me. I am a director of engineering at Scale AI. Scale's mission is to accelerate the development of AI applications. We got started with self-driving cars, doing a lot of data annotation and infrastructure for the autonomous vehicle industry. Since then, we've expanded to all sorts of different industries, ranging from use cases in vision, NLP, kind of disaster response and recovery, hospital surgery type applications, and including kind of providing models as a service for other customers as well. Before that, I had a computer vision startup building infrastructure for real-time video understanding that Scale acquired. And I was at Tesla on the Autopilot team before that, responsible for the core vision neural network. And throughout all that experience, there was a pretty big difference between what I was actually focusing on day to day as an industry applied machine learning practitioner versus everything I did in grad school and undergrad to kind of write papers and make models work well. And that's what this talk is about. It's about data-centric AI in practice. And so what is data-centric AI? So this is the discipline of systematically engineering the data used to build an AI system. So when you're learning machine learning in class, you're doing your homework assignments, oftentimes it's implement this part of an algorithm, get your metric to be this high, improve performance by this much. And this is an important way to make progress in machine learning. And in academia, we go a bit further than this. Most papers that get published are papers about a new way of modeling, a new way of approaching the algorithms behind machine learning, and they're evaluated on or on academic standard benchmark data sets. You kind of have to do it that way. Otherwise, how could you compare, is one researcher's result performing better than another, unless you have a standardized data set? In industry, it's the exact opposite. You can tweak the data set to fit your application as much as you want. And it turns out that it's actually way higher leverage to change your data to improve your model than to change your model directly. And so most time, doing machine learning in industry is in everything around the ML code, this small diagram you see at the center. There's the data curation. There's the monitoring of your models in production, the data annotation, making sure that your data is labeled correctly according to what you actually need, collecting it, verifying it, configuring everything, and getting it all working in production, and getting the loop back so you can keep improving it. And one of the reasons that this is so much more prevalent in industry than in academic machine learning is that the defining characteristic of real-world machine learning problems is long-tail distributions. So this is an example of a public self-driving car data set called Berkeley Deep Drive. And these are the different objects labeled in the data set. You can see there's a lot of cars, which is good if you're building a self-driving car. It's important to be able to recognize other cars. There's fewer traffic signs, traffic lights, people. But then you start getting into classes like buses and cyclists. And these are really rare. And this is for people who are building self-driving cars, where the bulk of the energy is going, is dealing with these sort of long-tail edge cases. And this doesn't really get reflected in most academic treatments of machine learning because if you want to improve your benchmark performance for your paper to get accepted to NeurIPS, that's only going to give you a 0.05% increase to do really well on cyclists. And so it doesn't really matter. But in industry, this is the defining challenge of being able to actually ship your machine learning models. If you went into a self-driving car that every time it approached a roundabout, gave up and got confused, it would not be a very useful self-driving car. And so very related to this is the concept of not all data being worth the same amount. So if you were a machine learning practitioner working on a self-driving car, you would much rather have the image on the right in your data set than the image on the left. And not only because there's stuff going on, but because there's actually really interesting stuff going on. You can imagine if you're a student creating a project deciding, hey, I want to build a self-driving car, you might tell your annotators, or you might annotate yourself, OK, I'm going to draw a box around every car in the scene. It's a useful way to start. You encounter something like this. And then you ask yourself the question, OK, well, how should this be annotated? So actually, I will ask people for a show of hands for two different options for how to annotate this data. One would be to draw a box around every car, including the cars stacked in this truck. And the other would be to not draw boxes around the individual cars in the truck and only draw a box around the car on the left and maybe a large box for the truck on the right. So option one, every car. Option two, only those two big boxes. How many of you think this should be better annotated with option one? How many of you think this should be annotated option two? OK, so we've got maybe like 80% going for option two, 20% going for option one. And this is precisely the problem, because you're going to have 80% of your annotators doing one thing and 20% of your annotators doing a different thing. And the worst thing is when there's inconsistency in how you're doing your annotation. Because then your model is going to be training, it's going to be given this example and saying, oh, well, I remember most of the time we were told, hey, we should just draw two big boxes. And then it's going to get a label where there's every individual car labeled. That's going to cause a very sharp gradient update for that model to say, oh, you got it really wrong. You got to make a big change here. It's really complicated. So this is one of the reasons machine learning is so hard, is that the real world is full of edge cases. And an exercise in annotation is almost an impossible task of taxonomizing the infinite complexity of our everyday reality. And so we can only hope to approximate that complexity and get close to it with reasonable annotation instructions, but building really balanced, sort of interesting data sets with lots of edge cases. So talking from that, the next natural question is how you decide what data you're going to collect and label. And usually when you start a machine learning project, whether it's an academic project or an industry project, you start by collecting some data, kind of in whatever method is most convenient. Right? Often we'll do random sampling on data we have in the field, or we'll just download a bunch of stuff and kind of work with that. And if you take your data and you randomly sample it from the world and you get it labeled, your model will work OK, but it will really struggle with those edge cases. So over time, people have realized, hey, actually, we could be a little bit more intelligent about what data we're picking to get annotated. And there's an entire branch of machine learning called active learning that's focused on this question, which is how do we prioritize the right data for annotation? What's going to drive the biggest model improvement? And you can see the sort of random sampling baseline is showing, hey, for a given annotation budget, how much accuracy can we get depending on what data we're choosing to label? That line looks almost diagonal. It's sort of very kind of suboptimal relative to these sharper curves, which are different types of active learning methods. And I'd say there's three broad categories of active learning methods out there. There's first trying to sample data based on diversity, so making sure you have reasonable representation of all the diverse sets of edge cases you can encounter in the real world. There's another based on model uncertainty. So you can actually run inference of a machine learning model before you have the data labeled. And you can look at what is that model saying as a signal for, is that model, are we going to benefit from adding this to our data set? So that depends on already having a model, but it's a useful mechanism for additional improvement. The extension of this, which tends to work much better, is actually to have multiple models and then look at where they disagree. So for example, you can take the same model architecture training code, and you can use 3 different random seeds to train 3 different copies of the same basic idea of a model. And then you can take what's called an ensemble, that ensemble of models, inference them on the same data point, and see, OK, is everyone on the same page about this data point, or did some think one thing and some thought another thing? When you have that kind of high disagreement between different models, then usually that means that data is really interesting to get labeled. And the third broad category of active learning methods is around expected model change. So this exploits our understanding of what actually happens when we train machine learning models, which is we compute a loss function, we compute the gradient of that loss with respect to the parameters of the model, and then we use that information to make small adjustments to the model parameters to improve performance on that data next time. And you can actually look at that gradient and see what it's calculating and see, hey, is this a small gradient update? You can take the actual, the absolute magnitude of that gradient update, or is this a large update? And that's another useful signal of, hey, is something really, really off here that our model could really learn from? So those are some broad categories of active learning methods, which are really important for improving your data sets. The next challenge you'll have once you start working on machine learning problems in industry is after you've decided what data to label, it's not going to be labeled that well necessarily, unless you use scale, of course. But just kidding. But actually, we do have pretty good quality. But the public data sets are full of annotation errors. So I think it's estimated that there's around 6% error rate for ImageNet. ImageNet's validation set. So it's like your teacher's grading your homework, and 6% of the time spazzes out. Very frustrating. Would be very frustrating to get a test where you're getting stuff right, and the evaluation says you're wrong. And a lot of sort of talk in industry is around, oh yeah, data is not necessarily clean, the labels are potentially mislabeled, that's kind of a problem. But the problem is much more acute than it's often given credit for, because the data tends to be mislabeled in precisely those areas of distribution that are most important to get labels for. It's those edge cases, like we saw earlier, where it's uncertain, should this be one box, should this be several boxes, where those labeling errors are likely to propagate. And that's exactly where you need as much data as you can get to improve performance on those edge cases. So the takeaway is that cleaning bad labels can meaningfully improve model performance. And there's some sort of theoretical derivations you can do showing there's a roughly kind of roughly quadratic relationship between the error rate in your data set and the penalty that your model is experiencing. So as the error rate goes up linearly up to a point, you basically encounter almost a quadratic penalty in your overall accuracy. And so given all these problems, given all these opportunities, as an industry, we're generally moving away from the concept of, oh, this is my individual ML model, and more towards, hey, this is my learning system. It's not just about what model I produce at one point in time. It's about how does that model continue to get better over time? How do we continue to incorporate more data? What is the overall loop, that pipeline where we can deploy something, get it out there, collect data back, make it better, and keep improving it? And so this quote from Andrew Ng is, I think, relatively relevant. Deployment is a process, not an event. And beginning deployment only marks the beginning of collecting more data to keep on updating your model. And so how do you actually measure the progress that teams make in getting towards that learning system? So is anyone familiar with the Kardashev scale? Raise your hands. Has anyone heard of this before? OK, a small number of hands. The Kardashev scale is a proposal for how to measure the progress of civilizations. And so a Kardashev scale measures how effective is a civilization at harnessing energy. Because in a deep sense, energy is the base input to all civilizational progress. Without energy, you can't do anything. And then with energy, it enables you to do everything you can do. And a type 1 Kardashev scale civilization can harness all the energy available on its planet. Type 2 Kardashev civilization can harness all the energy from its local star, so all the energy from its solar system. And a type 3 civilization can harness all the energy in the galaxy, which we're very far away from, but would be cool to see one day. And I think there's an analogous scale you can draw for how mature you are with your machine learning model development process, which is I call it a type 1 ML team, a type 2 ML team, and a type 3 ML team. And so I'll give you a set of heuristics that are useful for as you sort of build up a machine learning project and take it to production and improve it, how you can measure the quality of your infrastructure and your processes. And the first is around the cadence of improvements. So often we'll see in industry teams deploying and training a new model maybe around once a month. And even that is better than some cases where you just have a model and it's fixed. When I joined the Tesla Autopilot team back in, I think, 2018, it was very early in the transition to sort of machine learning driven life cycle. And so we would have a machine learning model, and that was kind of fixed. And then if we wanted to make improvements, we would change our post-processing code to interpret the model outputs better. And over time, we realized it's going to be a lot more effective to iterate on the model more directly, move more of our post-processing code into the model itself. So type 1 team is maybe shipping model improvements once a month. A type 2 team is shipping model improvements at least weekly. You have the infrastructure in place where you can actually collect new data, get it annotated, get your model retrained, evaluate it to have this happening on a weekly cadence. And then the most sophisticated machine learning teams are deploying continuously. So you don't actually have to have an engineer, a machine learning engineer, sit down and say, I'm going to go make a better model now. The system should take care of that infrastructure for you. When I was at Tesla, we had this concept of operation vacation, which is, can we build our infrastructure well enough that all of the machine learning engineers can go take a vacation? And as long as the labelers are still labeling, by the time we get back, the models in production would be better. I think it's a useful North Star heuristic for how good is your infrastructure if you can achieve something like that. And the reality is it's definitely achievable. It just requires investment, and it requires tooling, and it requires building. The second is around how you decide what data to label. And at the beginning, often people are labeling either all the data they have because they don't have very much, or they're randomly sampling some data to annotate. We see as teams improve, this big problem comes up, right? Which is you've trained your model, it's in production, and it's working like 85, 90% of the time, but not 100% of the time. And then suddenly your users start yelling at you about some edge case. Or sometimes your boss is Elon, and he starts sending angry emails to you that the drive is messing up on his commute, and you need to fix this edge case right away. And how do you deal with that? You can't write an if statement. If this edge case, let's handle it better. There's no mechanism for that that's effective and durable and sustainable in machine learning. So you really have to fix that issue by tackling the problem in the data itself. And so the first way people do that is they start to be able to manually curate these high-value scenarios. So being able to say, hey, we know we need more images of roundabouts in our self-driving car data set. Let's go find a bunch and then get it annotated. The type 3 teams use that highly leveraged manual curation and the automatic active learning strategies we were talking about earlier. The next type of maturity is around how you actually manage the quality of your data. And this is, again, a huge disconnect, I think, between data-centric AI in practice, what we're talking about in industry, and what we typically talk about in an academic setting. In an academic setting, you're usually given the data set. Cool, that's what you work with. In reality, some of the highest leverage you will have as a machine learning practitioner is in making sure the data you have is really good. And so that often involves looking through a lot of it yourself. Actually, out of curiosity, how many people have labeled any data for a project before for themselves? Raise your hand. Cool. About like 50% of the room. I think this is a very good practice to do, and I highly recommend everyone when they work on a machine learning project to either label a bit of data themselves or look through a lot of examples, because you're going to find things that you couldn't see in the statistics when you just look at sort of the evaluation metrics. And often what you find gives you insights into how to improve things, in a very meaningful way. So as teams move up in their sophistication, they often move from no QA process at all to having some manual QA process to make sure that the data that they're getting is well labeled. The most sophisticated machine learning teams bring their models into the loop for this process. So once you have a model, does anyone have any ideas how you might be able to use the model to spot incorrect annotations in your data? It's an open question. Say it louder.
Have a confidence measure of its prediction.
Yes, a confidence measure of its prediction. So maybe if the model is very unconfident in something, that data could be interesting. Or if it's confident and it disagrees with the label, that's maybe something worth looking into as well. And that we'll actually see a demo later in this presentation of some of the tooling that exists in industry for these type of problems where we can cover a workflow like that. Yeah, so confidence is a big one. Another big one is to look at the loss. You can compute how high is the loss for a given example. And it turns out, every time I've ever done this, and I encourage you next time you're working on a data set to do this as well. If you take all of your data and you just sort by loss, the highest loss examples are almost always just completely mislabeled. The labels are totally wrong, and that's why the loss is catastrophically bad. So that's another way to kind of use your models in the loop for quality assurance. And I think the last important axis of measuring your progress as a machine learning team is who is driving the model improvements. So at the beginning, it's just you're the machine learning scientist or engineer. You're working with the data, trying to try different experimental strategies for improving your model performance. You maybe are running a bunch of different cells in a Jupyter notebook. You get some models. You put their numbers in a spreadsheet. You find the best one. That's what you ship. Over time, you want to involve a data team as well. Folks who are actually really focused on the data itself and ensuring it's well distributed, it's well labeled, and using that resource to improve the overall model performance. In the limit, you expect the data team or individuals who are responsible for the data to be driving all the improvements for a current generation of machine learning system. And only the step changes, the crazy different ideas, the fundamentally new architectural approaches, et cetera, that's really the responsibility of the ML scientist. So I'll kind of take a sidetrack on how some of this gets applied in practice. One of the products that I work on at scale is called Nucleus. It's a data set management platform to help teams improve their models by improving their data. And so this tooling is really built for the computer vision sensor fusion domain, which it sounds like some of you have experience with. A lot of you are also maybe working with NLP data or tabular data as well. But often what happens is that no matter what data you're working with, you train your model, it's working pretty well, but it's not working well enough. And so what happens is you need to figure out where in the data distribution is the model failing. It's not enough to say, hey, I'm at 97 or 90% accuracy, I want to get to 93. You have to have a qualitative understanding of, yeah, this is safe to ship, or we're working well here, we're not working well here. And once you figure out where your models are failing, where in the distribution these problems are occurring, then you can actually go out improving them. And typically, as we've talked about, the highest leverage way to improve your models is to improve the data they're trained on. And so that can mean finding bad labels and fixing them, or it can mean prioritizing the right unlabeled data to label next. So I'll show a brief demo of what some of this looks like in practice. So this is an example. This is that self-driving car data set, Berkeley Deep Drive in Nucleus. And you might have an edge case that you're struggling to work on. And so the first thing folks might do is try to describe, OK, what is that edge case? In some case, we had a user who was talking about challenges with sun glare. So if the sun is shining directly in the camera, it actually makes it really hard to do object detection sometimes. So how do you find issues like that? So what we do in Nucleus is we integrate with what's called CLIP. Has anyone heard of this model, CLIP, before? I see a few nods. So this is a multimodal embedding model that was open sourced by OpenAI. And this lets you generate vectors for either images or text. And these vectors have the property that they'll be close by to each other if the input data was a similar concept. And by close by, I mean in some high dimensional space, right? Let's say you have a 256 dimensional vector. You can picture that as in a high dimensional space. It's a point. There's going to be another point for other images. And those 2 points will be close together if the underlying concept is similar. And what's really cool about this is if you can do this across modalities, so text and images, when you put in a sentence, the embedding for that sentence will be nearby the embedding for an image if the sentence roughly corresponds with what's going on in the image. So that's how this works under the hood. And to actually train these models, what's cool is you don't actually necessarily need kind of manual labeling. The way OpenAI trained this model was they scraped the internet, and they got a bunch of images, and they took all the captions that they could automatically parse for those images. And at a high level, there's a simple objective, which is to predict, given an image and a caption, did these belong together in the original data set, or did they not? Was the image had an unrelated caption, and this caption was from something else? And you can train a model that takes the image, converts it to an embedding, takes a caption, converts it to embedding, and then penalizes the model if the embeddings are close together, but they were actually from different parts of the data distribution, and encourages the model to pull the embeddings closer together if they were actually from the same original pair. So that's how these kind of multimodal embeddings work. And from this in Nucleus, you can kind of look through and see, yep, cool, this is a bunch of data that looks like sun glare. And this is useful. Often folks who are working on these kind of real-world problems, they want to add this as new metadata. They want to know, hey, OK, cool, can we get a tag every time something has sun glare in it going forward? And so the way we do this in Nucleus is with something called auto tag. And so this is a feature that lets you add arbitrary new structured metadata to your entire data set with a few examples. So, sun glare, auto tag example will be the tag name I create. And I'm giving it a few seed images. And then what's going to happen under the hood is we'll start training a binary classifier. So something that can just predict, hey, does this have sun glare, yes or no? And the training happens in real time. So you have to kick off the sort of a training job for a model that's going to take in these embeddings as input, and it's going to produce sort of a score as output, which is just 1 if as close to 1 as possible if it really looks like sun glare, and it's close to -1 if it doesn't look like sun glare at all. But I've only given it 4 examples, right? And we've talked about the importance of data and having a lot of high-quality data. So how can you actually learn a model with such few examples? Well, there's a few different ways. So one of them is instead of operating on the raw images, you can train models on top of embeddings. And these embeddings, because they're already learned from machine learning models that were trained on lots of data, they tend to be very representative, very descriptive of the underlying sort of semantic content of the image. And so with a few examples here, we can go through and say, yep, this is an example of sun glare that I'm looking for. This is exactly what I'm looking for. But you can see this literally says the word bright. And you can see why that's nearby in image space, because the model read that word and it was like, yeah, bright. OK, this is very related to sun glare. But this is not what we're looking for, right? This is not what we're looking for. So I'm gonna skip that. I'm gonna skip that. And by skipping that, I'm implicitly teaching Nucleus, hey, this is a negative example. I don't want this. I'm adding it to the negative examples in my training set. And when I click refine, we take all that feedback, and then we retrain and re-inference the model across the data set. And you can actually do this in a sort of a performant enough way to have a real-time web application because you're operating on the embeddings, as opposed to operating on the raw images themselves. And so you can do this. You can do a few rounds of refinement. In practice, we see that with a small set of examples, you end up with something that broadly corresponds to what you're looking for. And you can go ahead and commit this to your data set. And this then creates a job to write new metadata for all of your images in this case to describe, hey, is it tagged with sun glare, yes or no? How much sun glare is there? And so once you do that, you basically add this new metadata to your entire data set that you can start to query on. And so it usually takes about 2 minutes. So we can kind of look for data that's already here and see, OK, where are the images that we already tagged with this auto tag? And we can go through and we can find a lot more relevant data. And this is useful for adding tags, right? But it's particularly useful when you want to curate your unannotated data as well as your annotated data. So what you can imagine is you had someone complaining about your self-driving car not working when there's a lot of sun glare, You take an approach like this, you apply it to all of your unlabeled data, and then from there you can prioritize what's coming in next to kind of go get annotated. So you can query, intersect the query with like the unannotated data and see what's there. Look through a bunch of other stuff, and use this to basically curate what's going to come next for label. Oftentimes, when you want to curate what comes labeling, auto tags are a useful input, but again, it's insufficient. And so, going back to some of what we discussed around active learning, we have kind of an implementation in Nucleus where you can pick your sort of target budget for how much data you want to get annotated. Maybe we only want to annotate 5,000 images, and you can take your original data set size and say, hey, just filter it down to 5,000 that are worth annotating. And if we're, again, that type 1 ML team, by default, we might just use random sampling. But we can start to add other methods like diversity-based sampling, bring your own active learning algorithms that you choose, create filters on particular auto tags so that you make sure you have enough representation of, like, say, police in there. And bring these kind of down to say, hey, we want to like look through a very small subset of our data that has this. So here's some of the tooling that people use in industry for curating the right data sets to get labeled. And then once you get that data labeled, it becomes about figuring out where is your model not doing well. And so in this example, you can add your own models via API. And by the way, this is available for free for students. So if you're ever working on a kind of machine learning project and you want to kind of look through your data, you can just go to scale.com/nucleus. We also have labeling credits too. That was one of the things I found most frustrating as a student is all the project ideas I wanted to do, they involved getting my own data. And so I think for one final project, we were working on automatic classification of exercise form based on like squats and push-ups. And so we basically camped out in the campus gym with a Microsoft Connect. And we asked everyone, hey, would you mind if we record you while you do your workout? And then we brought a Google spreadsheet. And we looked at hundreds and hundreds of clips of different people working out. We became experts on form for squats. And then we would label 4 different attributes of what they're doing. And honestly, to build cool projects, a lot of times in machine learning, you do have to go get your own data. But we are trying to make it easier at scale. So we have credits for that as well. If you want data labeled for a project, please just reach out. And we can make it happen. So yes.
So the IDE.
Yes.
These features are very cool. The IDE, does that work only for images, or do you also do videos or video clips?
Great question. We also do videos. So Nucleus is designed broadly for computer vision. So there's kind of images, videos, and 3D point clouds. So let's see if I can find a good video example. This is one of like kind of short clips of videos, and these are public as well if you want to kind of peruse them. Also pull up that. So in this case, you have like clips of, in this case, someone is jumping. This is kind of an action recognition and object detection task. This is a collection of different stuff. People are often doing action recognition, object detection. And then 3D data tends to be especially interesting, where you're collecting, say, LiDAR point clouds from a laser that's spinning around, say, a vehicle, and measuring, using the time of flight, how far away objects are from the vehicle. And you want to combine that data with sensor metadata, and so with like camera metadata. And so these point clouds can be very, very large. You can have kind of multi-gigabyte point clouds with tons of information from all sorts of stuff and many different images in the same scene. And you often then need to be able to kind of interact and see, hey, show me, where is my vehicle versus the other different objects in here. And then if I were like looking at particular images, how does this sort of like correspond? So you can see, like in this case, we're projecting 3D data into the 2D scene. And this is using camera calibration matrices, which if you take a kind of geometric computer vision class, you'll learn all about. But it's a way of mapping stuff in 3D to where it would go in the 2D camera. So once you kind of get your data in, often you then need to get your models in. And so for folks who upload models in addition to their ground truth, you can start to see the predictions of these models, either side by side with ground truth, or in this case, the data is unannotated. So there's just model predictions as well. And so, often folks who are working on projects, they just want to look through a lot of examples first, qualitatively figure out, hey, what's going on? Looks like we have a false positive prediction of a person here. That's not good at all. And so maybe I'm going to select this image as we're going to need to go back to that. I can see here actually it looks like we're predicting the truck twice. One is a bus and one is a truck. There's something called non-maximum suppression that people use in computer vision to try to solve issues like this, where you can kind of merge bounding boxes if they're close enough together, but it doesn't always work. And so you can see this is maybe a bad prediction as well. And you can go through, you can do this manually, you can do it in bulk. We can look through a few more, see where it looks like we're predicting something on the hat here on the reflection. And mark these as maybe bad. Often you end up having to move away from the concept of one data set towards the concept of collections of many different scenarios. And this is especially important, when we talked about those edge cases earlier. Hey, we want to start tracking these edge cases particularly. And it's also important, when you're prioritizing what to label next and what to fix, et cetera. So in Nucleus, that concept is called a slice. So you can create a slice of data. This is like maybe my bad predictions. We need to fix. And we have a curated subset of data now that we can either, if it's unlabeled, we can send it to labeling by getting it labeled and adding it to our training set. That should probably help that data. We can also create a scenario test, which I won't get into too much right now, but this is a way to extend the concept of unit testing but to ML models. So instead of writing unit tests for code, when you're changing the data to improve your systems, you have to have some way of validating, did that actually help or not? And what's really challenging is with good code, usually we like to decompose it. So you can have independent unit tests for different functionally independent parts of the system. But if you're just training a big machine learning model on a bunch of data, even if you add more data to improve your performance on edge case number 1, you might be regressing edge case number 2, because now edge case number 2 has less overall representation. So this is really hard. This is an unsolved problem in industry. But one way to try to get ahead of it is to move away from the concept of one test set, move toward the concept of many different test sets, each evaluating a metric you care about, each where you maybe have some qualitative familiarity with what that part of the test set looks like, so you can kind of track that over time. So once we kind of go through these examples qualitatively, we can start to find issues right away. But oftentimes, it's much more efficient to find the issues quantitatively, right? And so we can go through, instead of looking at our data one by one, we can start looking at metrics on the data set overall. And so how many people are familiar with the concept of a confusion matrix here? Raise your hand. Cool. Yeah, sounds like basically everyone is. This is showing where our model predictions disagree with our ground truth on a class-by-class basis. And this is useful as a metric or to get insights in your model, but oftentimes when we're working with tools like this, in my experience in academia, they're relatively static. Cool, we have a plot, now what? One of the hallmarks of making these effective for actually driving improvement is to make them interactive. So you can actually go look through the examples of a failure of a particular case. So let's say I want to understand, why are we predicting, motorcyclists as pedestrians 7% of the time in my data? According to this cell in the confusion matrix, we have a big problem here. I can click on the cell, and I can go through on an object-by-object basis all of those individual failures and look through them. So here I can see, these are in fact, this is definitely a motorcyclist, not a pedestrian. So this is a bad prediction. We should have been predicting motorcyclists instead. And I can see that's the case for a lot of these problems. And this is sorted by confidence of the model. You can take that concept. What was your name with the confidence? Scott? Okay, so Scott's idea was we could actually look at where the model is confident as a way of potentially finding issues with our ground truth. So let's actually do that. So let's clear this, and let's look at only our annotated data. And I'm going to, instead of looking at intersection over union, I'm going to look at false positives. So these are cases where the model predicted something, but the ground truth said there was nothing there. And we can focus on, I guess we can focus on all classes, or we can focus on a particular class of interest. I want to go look through cars. And from here, I want to go further, and I want to say, we want to sort by descending confidence to see where our model is really sure there's a car, but the data says there's no car there. And you can see some of these, there's a car being predicted, and there's no ground truth at all. So what's going on? This obviously looks like a car. If we click into the data and we hide the predictions for a sec, you can see this is a classic annotation mistake, where the annotator just misdrawing this bounding box. So great idea, Scott. There are real issues here in public data sets that we are using for research every day that can be caught with these techniques. And then you can also see cases where there's actually just a class confusion. So in this case, it looks like the annotator labeled this as a truck, which is going to cause a lot of problems in your perception and in your planning stack if you behave differently around trucks versus cars. So these are some mechanisms that people use in industry to go away from just, hey, we're at 85%, we want to get to 90%, and more towards how do we really debug the failures that we have, and then how do we improve them over time. And so there's a lot more kind of tooling that people use to improve their model performance, but I would say the overarching kind of message of this talk is to go look at your data and make sure you have a real understanding of what is in your data set, that you're visualizing it, that you're exploring it, you're tinkering with it, maybe you're labeling some of it yourself, you're getting really familiar with it, because this is by far the sort of most impactful way to improve the quality of a typical machine learning project. And one other sort of comment is that unlike traditional software systems, which often when they have bugs in them, they just crash, give you a compiler error or runtime error, and it's very easy to see. Machine learning systems are both great and evil in that they're very resilient to bugs. So you can have bugs in them all the time. And rather than crashing, they will just be 3% worse, 4% worse, 5% worse. I've seen cases in industry where we were doing data augmentation, flipping images kind of left and right to improve performance by adding more diversity. And in some cases, the annotations weren't also getting flipped. And so you're penalizing your model for not predicting things that don't exist, right? They're on the wrong half of the image. And it would never come up in your metrics because you're just seeing, oh yeah, it's not working maybe as well as I want. Sometimes it is working as well as you want, and actually could have been working better. But until you visualize your data, it's really hard to see that. And you wouldn't even necessarily see that in a tool like Nucleus because this is sitting above the part where you do the data augmentation. So as a general rule, it's very helpful to be paranoid, be super paranoid when you're working on machine learning, and to visualize things right before the operation of interest. So for a neural network training, working on computer vision, you would want to visualize right before the forward pass. Like in your code, the line before, that's where you do it, because if you do it up front, there can be weird stuff that sneaks in the middle. So that's kind of the bulk of what I wanted to share on the industry perspective on data-centric AI. Thanks for having me, and I'm so happy to take kind of any additional questions.
I have some questions, but let's open the floor to the students. Any questions for us? Yes.
Yeah, so my question revolves around your classification of type 1, 2, and 3 anomalies.
Yes.
So it looks like the interface between type 2 and type 3 was not one necessarily of skill level, but one more of access to a robust CI/CD pipeline, where, like you mentioned, like active learning and fluid algorithm. So how long does it take to build that structure up for a team? And is scale directly contributing to some sort of generalized tool? Because it seems like a very valuable booster to put on a bunch of this.
Yeah, it's a great question. So the question is around how long does it take to move from type 1 to type 2, type 3 ML team? And is this a question of skill level, or is it a question of infrastructure, tooling, time, investment, et cetera, and what is scale doing to kind of help with this? So I would say definitely the first order challenge of moving from a type 1 to type 3 team, it's not about your talent, it's about your investment. And have you put in the time to build these systems? Because the most talented machine learning practitioner in the world, when they get started with a project, they're not going to have any infrastructure to go off of. So everyone starts as a type 1 ML team. And in reality, it takes a really long time to kind of get up here. I would say very, very few teams in industry, even in the most sophisticated organizations, could really be called type 3 ML teams. It's kind of something aspirational where we want to get to, but often it's really hard. It's just really hard to get that infrastructure in place. And it takes a lot of engineering time, it takes a lot of tooling, investment. So that is one of the reasons that Scale works on these set of problems is we see a broad landscape of people working on ML across different industries, and they all have very similar problems when it comes to the tooling. So that's kind of why we try to help with that. But I would say to move from a type 1 to a type 2 team, it can take 6 months, a year, multiple years, depending on your setup. And then again, the same for moving to type 3.
Question? Yeah. Yes.
Is there a limit to the quantity of data you use, or should you rather focus on quality? Since, as you explained, flipping of the image create type of problem rather than providing better system.
Yes. Love the question. So yeah, do you focus on quantity or quality? So the first thing I'll say about quantity is that quantity has a quality all its own, which is that so all else equal, you tend to get better performance the more data you have. And there's a very robust set of literature that shows roughly a logarithmic relationship between the amount of data you get and the model performance you incur. Which means, in other words, if you want to kind of get linear improvements on your metric that you care about, you have to get exponentially more data. So that's a useful thing to know about. It obviously doesn't scale at some point, right? It gets very expensive to keep doubling. But that relationship holds even at enormous scale, where you have data sets in the hundreds of millions or billions of data points for like large, complex unstructured data, like images and videos, where that relationship still holds. So more is always better when you can get it. But the higher leverage bit often is in the quality. And so if you think about the real world as being normally distributed, the ideal data set is more uniformly distributed, where the edge cases are as represented as the main stuff. And that could be in how you collect the data, it could be in how you label it. It could also be what you do at training time. So a very common strategy for dealing with long-tail distributions is to oversample rare data at training time. So your model sees more of that as it's learning.
From a computational standpoint, is it like doesn't make sense to add more layers to the neurons, or is it better to focus on quality of data?
Yes, it's a great question. So when do you kind of like add more layers to your neural network versus focus on data quality? So first of all, I'd say data quality focus always helps. It doesn't necessarily matter how big your model is. If you invest in data quality, you'll see pretty big gains from that. As far as how many layers, more layers. Has anyone seen the meme? More layers. Just add more layers. That's like the data scientist approach. But in practice, there is actually there's a set of papers called sort of scaling laws papers, originally from OpenAI, and then other people have built on them, showing pretty precise mathematical relationships between the optimal amount of parameters to have for a large-scale deep learning model relative to the size of the data. There's a paper I'd point people to called Chinchilla, if you're interested in this. I believe this was it was a more recent paper showing very precise scaling laws and showing that some of the largest models that people are training today are actually dramatically sort of inefficient because the balance between the data and the amount of compute they were using and the amount of parameters they had was totally suboptimal, and you could actually train a much smaller model and get similar performance. And that was what their theory showed, and then their empirical results demonstrated it. So it's useful to pay attention to, it doesn't always help to add more layers. And in fact, if you don't have enough data and you add more layers, sometimes it can increase the tendency of overfitting.
Yeah, so back to that idea of like creating data slices and then creating like model unit tests kind of out of them. If I'm using Scales products, is there a way for me to integrate that into like model deployment? Can I halt my model deployment if it fails unit tests, or can you just elaborate more on what I do there?
Yeah, absolutely. The question was, how can you integrate those types of unit tests into model deployment? And the answer is certainly. So most people who use those unit tests, you might create them via UI because it's convenient, but in practice you use them day to day via API. So you can define sort of API endpoints. You can run in Circle CI or whatever CI/CD system you use to say, hey, when I've trained a new model, I want to run it through my evaluation pipeline. And part of that is going to be not just looking at my validation test set score, it's going to be looking at my unit test performance. And one question that comes up then is, well, like, do I have to pass all the unit tests? What if I'm doing a lot better on some unit tests and then worse on one or two? And this gets really hard. And actually, as teams get more sophisticated, sometimes the rate at which they can ship new models slows down because they have more and more metrics they start tracking, and they can't regress on any of the critical ones. And so it becomes increasingly sort of paralyzing to kind of hold yourself to not letting anything go. So it's important to track, and it's also important to recognize when it's helping your velocity and your overall performance versus when it's hurting. One rule that I've seen some teams implement in industry is to actually set a hard cap on how long they're going to spend sort of training and validating a model. And they're going to say, even if you could have gotten me a better model with like more training time, the net cost of having a cycle time that's in months instead of weeks or days for our organization is higher than the individual benefit. And I've seen this firsthand. When I was an intern originally on the Autopilot team at Tesla, I trained this very bespoke model where I kind of spent many days training a base model, and then I manually changed some hyperparameters, and I fine-tuned it a different way. And then I changed more stuff, and I changed the data, and I took that model and I fine-tuned it. And it was like basically 3 weeks of this very esoteric pipeline, and it crushed all the metrics. And so we shipped it, and the model was in production, and it was great because cool, the model is better. And then it became really frustrating for the entire team because we just could not improve on some of the performance that we needed to improve to ship another one, and it actually made it really challenging to continue to make improvements over time. So that's another way to think about unit tests.